This is the 5.8 green worksheet. Number 3, problem about the Richter scale, and this is a classic example of how logs are used in that so-called real world. All right? The Richter scale is a numbering system that measures how intense an earthquake is. So the Earth normally has an intensity like normal. Did you know that even though you can't feel it, the Earth is kind of moving? Can you feel it? Can you feel it? Whoa. It's actually somewhat vibrating, right? But very, very minimally. Now, what numbers should we assign to not much vibration at all? I like 1. Here's why I don't like 0. 0 might make sense to you because the Earth is not shaking. There's no earthquake, so there's 0 movement, right? However, the Richter scale goes like this. R could be 1. R could be 2, 3, 4, 5, 6. So that's the Richter scale number. And the Richter number tells you how strong or how intense or how much the Earth is vibrating relative to normal, right? Like this many times as much. Well, if the base number was 0, right? If this was a 0 down here, if that was a 0, that wouldn't work. Because if the Richter scale number was 4, even though I'm going to prove this point wrong in a moment, let's say that that meant that it was 4 times as strong as normal, right? That's not, how would that work then? What's 4 times 0? 0. That's why we can't use 0 as our base number. So instead, we use 1. So normal will be assigned not 0. How about, what if we called it 10 to the 0? Instead of 0, could we call it 10 to the 0? The Earth is not shaking. We'll assign it a value of 10 to the 0, which is what? 1. Okay? That is basically what in this problem is I sub 0. I sub 0 is the initial intensity of the Earth when not much is going on, when there's not an earthquake happening. So as we read through this problem, which I'd like you to do now, think about I sub 0 as being normalcy, no earthquake. So if you've read the problem, you see that I sub 0 is that base amount where the Earth is normal. As you work your way up the scale, you might think, well, let's say that one earthquake had a Richter scale rating of 6, while another one had a Richter scale rating of 3. Do you think that that means that earthquake A is 2 times the strength of earthquake B? Because one was 6 and one was 3. So it's 2 times as strong. That would make sense, wouldn't it? 6 is double 3. It's wrong, though, because here's how the Richter scale works. It's not just a number. Those numbers aren't just numbers. They're actually exponents. As you work your way up the scale, 1 actually means 10 to the 1. And 2 actually means 10 squared. And 3 means 10 to the third. 4 means 10 to the fourth. 5 means 10 to the fifth. And 6 is 10 to the sixth. So if you had a Richter scale number of 6, that means that that earthquake is 1,000,000 times the intensity of normalcy, of the normal vibration of the Earth. If you had a Richter scale number of 3, what does that equal? 1,000. That means that the shaking going on in that area is 1,000 times the strength or the intensity versus normal. All right? So how would you compare this one to that one? How many times stronger is a Richter scale 6 versus 3? You don't just divide 6 by 3. You divide what? 1,000,000 by 1,000. We need to divide 1,000,000 by 1,000. Or if you know your exponent rules, divide this by that What do you do with exponents? Subtract. So a Richter scale rating of 6 would be 1,000 times the strength of a Richter scale rating of 3. Okay? Now, they're going to ask you to compare the earthquakes that were in Turkey in 1999, one in Western Turkey, one in Adana, Turkey, in 98. So they want you to compare a Richter scale rating of 7.4 to a Richter scale rating of 6.3. So instead of going through the process and using the log formula, basically, here's what we do. The Richter scale rating of 7.4 means that the actual intensity is 10 to the 7.4 times I0. What's I0 again? 1, the normal Earth's the normal vibration level of the Earth. Okay. Meanwhile, over in Adana, in 1998, the Richter scale rating was 6.3. That means 10 to the 6.3 times the normal vibration level of the Earth. I'm simplifying some of these terms and such for the purposes of this class. If you were an actual earthquake studier, right, it would be a little more, yes, there'd be a lot more jargon that I'm not using. Yes. It's really just one. And in fact, to compare the two, we divide them, right? To compare this earthquake to this earthquake, we divide them. True? Remember how I did that with earthquake A and B? I did 1,000,000 divided by 1,000. We're going to do that here. You're going to take 10 to the 7.4 divided by 10 to the 6.3. I left out the I sub 0 because you said it's just 1. It's close to 1. Regardless of what it is, what happens when you divide? They cancel out, okay? No matter what that number is. So let's finish the problem. This is part C. What's 10 to the 7.4 divided by 10 to the 6.3? Give me it as a power of 10. 10 to the 1.1, calculate that. 12.59, let's call it 12.6. That means that the earthquake in 1999 was 12.6 times as strong or intense as the earthquake in 1998. All right? That's significant. 12 times as strong. If I said, well, I just won $1,000, and you said, well, I just won 12,600, that's a powerful number, right? 12.6 times the strength, right? And now we're talking numbers even bigger than that, because this one would have a strength in the millions, 10 to the 6th, right? This one would have a strength in the 10 millions. So we're talking about some massive earthquakes in Turkey in the late 90s.